What we've got happening here on the bench, I've got an isolation transformer, which is 240 volts input and 240 volts output, but I have no earth connection on the output. And that's an important point to understand, because in our circuitry, just hold this up, and in our circuitry, if I did have this signal generator earthed, I would not be able to put this sensing resistor here, because the earth from this test point here, which is connected to the oscilloscope chassis ground, would also be connected to this point on the signal generator ground. And the whole experiment would be useless. It would not work. So having the equipment floating is a big advantage. Now, I first of all tried to put batteries to run that, and then when I opened the equipment up, I realised that was never going to happen because the power supply inside is too complex. So the next best thing, of course, is to use an isolation transformer and just be aware of the hazards and be a little bit careful with that. In our last action-packed adventure, we looked at the parallel RC circuit for current phase shift. We looked at the capacitor current and we compared that to the resistor current, and we found out that we had 90-degree separation between those. A little bit difficult to do in a parallel RC AC circuit. We had to use current sensing resistors and use 2 channels of the oscilloscope and use those proportional voltages that we measure across each resistor, use the voltage drops, and that gave us an equivalent current. We did some calculations to map out the currents, and after we ran the lab, we in fact got almost identical currents, and our supply current worked out to the vectorial sum between the two. Today we're doing a slightly different version of this lab. I've called it a tricky lab to do, so it's only a demonstration, and the video serves quite well to show exactly what this is all about. I've dragged the circuit down from the previous laboratory, and this time, instead of looking at the resistor and the capacitor current versus each other with respect to ground, I put a common ground at this point, and I've also now added a sensing resistor in series with an ungrounded piece of test equipment. Now, the problem here with this ungrounded situation, a lot of students have difficulty understanding what this is all about, can't understand that it's difficult to measure anything to do with the supply current in this circuit without having this floating. Well, I've drawn the earth here in a dashed green line, and of course if this is grounded and this point's grounded, any resistance that we put in between these 2 points will be short-circuited and we won't be able to measure a sensing current. Likewise, if I was to put a sensing resistor up here, I need a common point on the cold end of that resistor to have a common ground to measure my resistor current or capacitor current against that. So I cannot put the part up here to sense the current. So I've kept it down here, simply floated the test equipment. We have the same Rigol oscilloscope, and we have it measuring IR and IS in this case now, current of the source. We'll swap channel 2 over to measure IC. So we'll have both IC and IR that we can plot against IS. And that's exactly what I discussed in the first video, part 1. That's a difficult thing to do. And of course you can't do it unless you have floating test equipment. So we'll measure the 2 parameters at a time, IS against IR, IS against IC. We're going to come out with figures that approach 60 degrees and 30 degrees. So I've written these in here like approximate 60, approximate 30. Here's the equipment that we're using. It's an Instech SFG series. I've got a couple of different series of these. They're all very similar. There's the printed circuit board inside for where the IEC, International Electrical Connector, comes in the back, goes through a safety fuse, and has the two mains wires and the ground connection coming across onto the main board. I do like what they do these days. Instead of bringing the mains right up to the front panel, we have an extension push arm with a switch down here to power this equipment on and off. The equipment, I must admit, is built very nicely inside. It's the first time I've had one of these apart. There's two boards, one for the front panel, one for the main panel. Quite extensive power supply mapping on here. There's at least two main low voltage power supply sections. It looks like I've got a dual rail down here and perhaps another dual rail up here, but at higher current. My original plan was, when I opened this up, I thought I might be able to power this board with a couple of gel cell batteries, but no, it's too complicated. So then the only thing to do was to float the supply. Again, here's my 240 volt connection jumping across to the main board. Never ever leave equipment like this open when you've got it connected to the mains, because you've got 240 volts down here, and whether you're using an isolation transformer or not, it's going to be a lethal voltage for somebody to come in contact with. Fact remains, of course, though, without an isolation transformer, it's even more dangerous, because if you're standing on damp ground or something and you come in contact with that and there's no safety switch involved on the power board, you're going to have a direct circuit from active straight down to ground, so it's even more dangerous. With the isolation transformer, I've said there's no ground connection to the chassis from the mains. That's in our case. Normally there still would be, but I've had to ensure that I've isolated that earth completely to have the gear what we call floating. So it's done temporarily in this case to allow the demonstration to work. Because of the multiple earth neutral system for power distribution, the earth is connected to the mains neutral at the power board, and therefore active, neutral, it has a respective connection to ground. And isolation transformer removes this connection for safety, and I do love this illustration. Because in the power board, neutral and ground are tied together with the neutral link. If somebody comes in contact with the active side of the circuit and they're standing on ground, bang, they've got the full 240 volts potential flowing straight through the body. Very, very dangerous situation. And without a current sensing situation like a safety switch in situation in the power board, you're going to be electrocuted. In this isolation transformer, the secondary has no respective connection to ground. It's completely floating. So that allows our guy here to be holding on to this 240 volts in this resistive circuit and standing on ground, and there's no connection between the 240 volts and ground, so theoretically he's going to be quite safe, providing we've got some high resistance happening in this transformer. So we use this isolation transformer a lot in the workshop for working on gear which is open. It just makes it much safer to do so, because we isolate the power transformer in the equipment we're working on from the mains. And also, a lot of equipment these days has switch mode power supplies, and they're even more dangerous to work on if we do have a direct connection to the mains. So we want to get away from that. We want to use, isolation transformer, and of course, these days, for the last 30 years, I guess, the ELCB or the RCD is required by law to be fitted to all power boards. But if it's an old board, don't rely on it being there, and think about getting one of these isolation transformers. They're nice to have in the workshop. Here's the circuit for the isolation transformer. We've got a beautiful transformer here with high voltage isolation between the primary and the secondary. So there should be no breakdown there, and that allows me just to use twin core flex straight into my equipment. No ground in this case because I do need the equipment to be totally floating. There's a picture of our 240 volt isolation transformer here. The secondary is much lower current. The primary from the mains is going to be rated at 16 or 20 amps, depending on the circuit breaker. The output from this is rated probably at less than 1 amp. It's quite small windings in the secondary. It's only designed to supply small pieces of equipment like this. Again, here's our phasor diagram. And this time I've put some more notes onto this because these are what we actually measured. Between IC and IT, I measured a delay of 424 microseconds on the oscilloscope, you can see in the video. The maths on that would be 0.424 over 1.25, the 1.25 milliseconds being the reciprocal of 800 hertz. Multiplied by 360 degrees to give me 122 degrees. In the red circle here, I've got to go 180 degrees minus the 122 to get 58 degrees. There's my 58 degrees showing there. IC leads IT by 58 degrees. On the other side, when we looked at IR with respect to IT or IS if you like, the source current, I measured 520 microseconds of delay. Again, that would be 0.52 divided by my 1.25. No need to use microseconds and milliseconds there. I've put it all into one unit. So I've said like 0.52 milliseconds divided by 1.25 milliseconds. The milliseconds cancel out. That's why I haven't got them written there. Nice, easy maths. Always try and keep it simple. Times 360 degrees. I get 148 degrees. 180 minus 148 degrees to get 32 degrees. There's my 32 degrees. 32 degrees plus 58 degrees adds up to, bang, 90 degrees. So the maths all stacks up perfectly. Why is there a difference, I've asked here? 26.7 degrees we calculated first of all for theta. I've got 32 degrees. Well, I've asked this question here. Does the output of my signal generator remain at 50 ohms at 800 hertz? Definitely no. That will increase. The source resistance may well increase to 300 ohms at higher frequencies. And that's going to change the complexity of my circuit quite a bit. Additionally, we added extra resistance in 3 parts of the circuit. I had a current sensing resistor here, here, and here. So I've made a much more complex circuit by doing that. It's only a subtle difference, but when you think about it, 27 degrees to 32 degrees, that's only a subtle difference in degree, phase angle as well. So all of those differences would have to be mapped into the circuit, and then you'd have to do translations between parallel to series, series to parallel to come up with the correct angles in each section. Why was there 180 degrees minus XXX degrees to see an angle out of 90 degrees finally? So why did I have 122 degrees? Why did I have 148 degrees? I needed an angle out of 90 degrees, not an angle out of 180 degrees. I'll leave that to you to think about, and maybe you should reinvestigate the circuit. Just have another look at that circuit there and have a think about why across here I'm getting a delay between the source current and either the capacitor current and the resistor current of an angle out of 180 degrees and not an angle out of 90 degrees. You can see here in the new circuit, I've got a common earth, and I've still got my current sensing resistor here and here coming from the capacitive part of the circuit and the resistive part of the parallel AC circuit. And now, because of my floating AC signal generator, I've been able to put a third sensing resistor. All of these sensing resistors are 10 ohms. You can see them there pretty clearly, I hope, in the circuit which is in front of the camera. So what I'm doing here, I'm measuring on one channel on the oscilloscope the current going through the resistive leg of the circuit, and on the other channel of the oscilloscope I'm measuring the signal generator current, which is the supply current. And of course the supply current here should be leading the resistive current in the circuit. So let's have a closer look at that. All right, we've moved right along now, and I've got the waveforms showing on the oscilloscope. First thing we need to do is just make sure that we've got both waveforms centralised around the middle of the screen, so I'll just do that. Doesn't really matter too much about the amplitudes, providing they're not off the screen. But even then, you know, if we're only looking at the slopes or something, that's not a big problem either. I'm going to use the cursor controls here, and I'm going to just shift that cursor back onto the upward part of channel B, and I've already got the cursor set here on channel A. If I'd had to do that again, I could have done that. There you go. Showing that we've got 520 microseconds. We can actually bring up a measure menu for that though. We can come into this, and pretty smart, these digital oscilloscopes. We can do that. We've got 147, 145, 146 degrees. Of course, we could run the maths on that. That would be 520 microseconds divided by 1.25 milliseconds times 360 degrees, and that should actually equal that value there. Now, why we haven't got an angle out of 90 degrees, you've got to be a bit careful reading things on the oscilloscope, understanding which quadrant that you're working in. So we'll come back and we might talk about that a bit more later on. What I'll do now, I'll just move things around a bit here. I'll shuffle my circuit to go across and measure the current going down through the capacitor leg. All right, now what I've done, I've moved the oscilloscope across to measure the capacitor current, and I've got some new waveforms on the screen. I've just got to set them up, so make sure that the two waveforms are centered over the middle axis. And then we've got to use the cursors to make sure that we've got the correct point set on each waveform, that we can measure the time difference again between these waveforms and work out a phase difference from that. So cursor, I've got one of the cursors set there. All right, let's put our yellow cursor down here on the yellow waveform where it's heading upwards, and now I'll switch across to the blue cursor. Bring that down to there, and all right, that looks pretty good. 424 microseconds there, and we can either run the maths on that, or we can use the measure function on the oscilloscope. So bring up the measure function, time there on the Rigol oscilloscope, and I want that menu there. And 230, no I don't, I want the other one. That one will do. 122 degrees, I'll call that at. Yeah, 122 degrees. So now we've got the difference in phase, the difference in time between the supply current going into the circuit, and we've already done previously the current running down through the resistor, and now we've done the current running down through the capacitor. So it's probably time to go now and have a closer look at that on the phasor diagram and map those vectors and just see if we've got the right angles. 1, 2. Okay. I'm just going to get in the scene, yeah. Okay, so what we've... Squeaky shoes! Oh no! Get rid of those shoes! Wear slippers for the next take. Okay. So...